So yeah, yeah, I think what I said here, this one here. Okay, I think I wanted to say something different than I did in the last lecture. What I wanted to tell is essentially what we have here on this slide. It's yet a different approach how to compute the fragments or a fragment's depth value in the fragment shader. Okay, I have said that of course we could for every vertex compute the z value and then just let this z value be interpolated by the rasterizer as an additional per vertex attribute, and so then it's made accessible by or in the fragment shader. Now that's clear, we can do that, but another method is as shown here. So what we do here, now we have a vertex shader program, and this vertex shader program just transforms the vertices with a modeling matrix, with a viewing matrix, and with a projection matrix, and then just stores the transformed vertex coordinate in the output dot def position. And so now this transformed vertex coordinate is now assigned to every vertex. It goes into the rasterizer, and the rasterizer then just for every fragment that is generated interpolates these transformed vertex coordinates to the fragments. And in the pixel shader that now works on the fragments, I can just use this information in order to perform the final division by W, by the homogeneous coordinate in that pixel shader. Now, so this position, this operation here, that is the operation that is always performed by the rasterizer. So there's no need to perform it in a pixel shader because the rasterizer does it. I just want to show here that, of course, if you want to make use of that value in your pixel shader as well, you can, of course, also compute it by hand and then do whatever you want to do with it. And so how it works here is simply that now a fragment comes in, and that is the input parameter here, that is one fragment. We have computed for every fragment. The rasterizer has linearly interpolated the transformed vertex coordinate, and now you can just read out from the depth position at which, in which the variable in which the transformed output position is stored, and from this depth position you can now access the z value of the transformed vertex divided through the w value of the transformed vertex, and you can then compute the depth value, and you might want to use it for whatever purpose. Just as a well, I would not say useless example. Sometimes you want to do what we do here, but typically, of course, because the rasterizer already performs this operation here, there's no real need to do that in a fragment shader as well. So now that we have discussed the depth buffer, we also have to look at what happens if multiple fragments fall into the same pixel, but these fragments are not belonging to opaque objects, but to semi-transparent objects. You see that here, for instance. You have this background, and then you have this circular object here, and this circular object is rendered so to say, in front of the background. The circular object has a certain transparency, or maybe we look at this here, and you see now that initially you can guess that this circular object has the same color as the one here, but because that one here is made more transparent, you see contributions now from the background which shine through, and they are somehow mixed with the color of that circular structure. You see it also very nicely here. So the yellow sphere, and through the yellow sphere you see the background. So the background is shining through, and the color of the background is somehow mixed with the color of the circular structure. And we now have to talk about how this can be realized, because so far we learned, okay, in case we have opaque objects, only the color of the one closest to the near plane is kept. Everything behind is discarded. We don't see it. But now we have semi-transparent objects, so we want to have this kind of shine through. Yeah, note that the depth test discards all but the closest fragment and shows its color. And the solution is now, in order to also handle these semi-transparent cases, that we simply disable the depth test, and then we need to blend together the colors of all fragments falling into one and the same pixel. But in order to do the blending properly, we have to render the objects in a certain order. First of all, what we refer to as blending, this is this kind of color mixing we have seen on the slide here. The mixing of the yellow color of this circle here with the background color. Now, this kind of mixing is called blending, and the blending essentially tells us how the incoming fragment color, the so-called source color, is combined with the color that is already in the color buffer, that is the so-called destination color. We have on current graphics APIs, in current graphics APIs, we have different blend functions. So we can select from a variety of different functions in order to carry out the blending of the source and the destination color. We will look into a particular blending function later on. And of course, pixel colors can also be entirely replaced, then no blending at all exists, or we want to blend and then we combine the source colors with the colors that are already in the color buffer. And here you see an example where such a blending is performed, and you see here, for instance, in the forest here, there's almost no blending, and then you see here, in the water now, the background image of the ape here is blended in some regions, in some other regions it is not blended. So you can also make that blending then adaptive to the content of, or to the colors which are blended together. We call that blending also alpha blending, and as I said, alpha stands for the opacity of a certain structure. And alpha blending simply means that we now blend two color contributions by considering the alpha values, the opacity values that come with these two color contributions. The alpha value corresponds to opacities. Typically, we assume them in the interval between 0 and 1. And as I said, 1 means completely opaque, 0 means completely transparent. And between 0 and 1, we have some semi-transparency. And what this alpha value from a physical point of view does, it indicates the percentage of light from behind that is blocked. Now, if a structure has opacity 1, then it means 100% of the light that comes from behind, from the background, is blocked. Nothing comes through. We don't see anything of the background. If the alpha value is 0, then it means 0% of the light that comes from behind is blocked, meaning I see all of the light that comes from behind. I see all of the background. And in between, I have a certain percentage of light that is blocked. The example here we have looked at before shows that kind of alpha blending again, where we have just different circles with different opacities. You see here that circle seems to have a rather high opacity, also the one here, and that one here seems to have a very low opacity. Or here, for instance, you have a nice example from scientific visualization, where we have a CT scan of a human hand. And for instance, here, in order to reveal the interior structures, but also still keep some context information in the surrounding given by the skin, we modify the opacity of the skin so that it's rather opaque here in this region, and also here, and also here. And then towards the center here, the opacity of the skin is continually reduced, and we let more and more the background or the interior structure, in that case here, shine through. No? So that is a very practical example where alpha blending, no, or opacity-based blending is used in order to reveal otherwise hidden structures. So now, how does alpha blending works? No? Because if we now have two objects with different colors and different opacities, we have to think about how do we actually blend the two colors to a final color, by taking into account the two colors of each component and their opacities. No? And let us assume here that we have two objects, the first object with the color 1 and then alpha 1, and the second object with the color 2 and alpha 2. And we assume that object 1 is before object 2. No? So, with respect to the viewer. And now we consider the colors and the alpha values to blend the two objects correctly. So, and here are the blend equations which we use. And the blend equations now tell how the final color and also how the final opacity is computed by mixing the two color contributions and the two alpha contributions. And in that mixing, of course, we have to take into account the opacities of these two contributions, no? Because it's clear if one of those objects has if the object 1, which is supposed to be before object 2, if this has a very high opacity, then nothing of the second object will be seen or will shine through. But if it has a very low opacity, then of course the contribution of the background object 2 will be rather high. Okay, so now what do we do? Now we can just split this right-hand side into two parts. The first part says, okay, let us assume we only have object 1. What is the color? And we also call this often the effectively perceived color. What is the color of this effectively perceived color of object 1? Well, we have said object 1 has color C1. No? This is just an RGB color. But now object 1 also has an alpha value. Okay, now you can imagine what would you see, no? If that alpha value is 1. No? It's clear, then we see, so to say, the pure color C1. But now what would you like to see if the opacity of that object 1 is 0? It is completely transparent. No? Then you would not see anything. It would just become invisible. A completely transparent object doesn't have any, so to say, self-color. You don't see any color of that object. And in between, if the value of alpha is in between 0 and 1, you just see a certain fraction of the color. And we realize this by saying, okay, the effectively perceived color of the first object is just its color times its alpha. Now we modulate the color by the alpha value. And then we could ask, okay, and what do we see of the second object? And first let us answer the question, if we would only have the second object, then the effectively perceived color of the second object would be its color C2 times its alpha 2. But now comes into play that of the effectively perceived color of object 2, a certain fraction is attenuated because object 1 is lying in front of that object 2. And that occurs here in that, we don't see it because I have a red pen, in that area here, that overlap area, in this area now, the effectively perceived color of object 2, in our example the blue, is attenuated by object 1. Now the question is, how do we actually take account of this attenuation? Well, we have said, that was what we said on this slide here, the alpha value indicates the percentage of light from behind that is blocked. And now we could say that 1 minus alpha is then the percentage of light that still goes through. And that means we take this 1 minus alpha of the foreground object as the attenuation factor of the effectively perceived color of the second object. This is then the blending equation for the colors we use. Now we just say the effectively perceived color of object 1, the foreground object, plus the effectively perceived color of the background object, but because the background object might be occluded by the foreground object, some of the effectively perceived color of the background object will be attenuated, will be blocked, and the attenuation factor is just 1 minus the alpha of the foreground. Now, does it make sense? Yes, it makes, because now if you consider that alpha 1 is 1, then the effectively perceived color of the object 1 is just C1, plus then comes 1 minus alpha 1, which is then 0, meaning that I modulate the effectively perceived color of object 2 by 0. Which is clear, no? That is what I want to achieve. If my object, the foreground object, is completely opaque, alpha 1 is 1, then I modulate the background with 1 minus 1 is equal to 0, because nothing will then shine through. If this alpha 1 is 0, then I don't see anything of the first foreground object, plus 1 minus 0 is 1, so I perceive the effectively perceived color of the background. And in between, I have a blend between these different color contributions. Yeah, and the very same blend I also now can do for the opacities, because it's clear if now two objects with certain opacities are blended, then I also get an opacity increase. And the final opacity is then also blended using these two opacities by just saying, okay, the final opacity is just the opacity of the first object plus the opacity of the second object, but because the second object is behind the first object, I modulate the second opacity with 1 minus the opacity of the first. So this equation, or these two equations, these are, so to say, the fundamental blend equation which you make use of if you blend objects with semi-transparencies. And you see, of course, that also if you have alpha values equal to 1, that they are handled correctly, because as soon as there's a foreground object which has an alpha value of 1, or whatever comes behind is weighted by 1 minus that value, which is then 0, meaning that you will have no contribution from any other structure which is behind that opaque structure. Yeah, the example here demonstrates how we actually apply these equations. Let us assume we have a color red 100 for the first object and an alpha value of 0.8 for the first object, and the color 001, blue for the second object, and an opacity 0.5 for the second object. And then how does the blending looks like? The color blending is then just alpha 1, which is 0.8, times the color of the foreground object, which is red, plus 1 minus 0.8, that is the 1 minus alpha 1 here, times alpha 2, which is 0.5, times the color, which is blue, of the second object. Then this gives a final color of 0.8, 0.80, and 0.1. And we do the very same for the opacity. The opacity is just opacity foreground plus 1 minus opacity foreground times opacity background is just 0.9. That would be the resulting color here in the area, in the overlap area between these two objects. In the other areas, of course, where only one object is rendered, no blending occurs, meaning that the pure colors of the foreground and the background object would be visible. Yeah, and now what you see here by looking at these two blend equations, blending is not commutative. If I would now assume that instead of the red object being in front of the blue is in front of the red, then I have to consider the inverse order, so to say, with respect to the distance to the viewer. I have to consider this in the blend equation. Then I have to exchange alpha 1 and color 1, no, with the color of the then foreground object blue, and alpha 2 C2 will be then the color of the background, the new background object red. No? So meaning that if I change the so the order of the objects, no, depending on the distance to the viewer, no, or if I change what object is the foreground and which object is the background object, then I have to reflect that change also in the blend equation, no? Meaning that blending is not commutative. The order in which the objects are blended together matters. Yeah. So, how does it now, or how is it now realized, that blending, no, in the fragment processing stage, no? So how can we do that? So yeah, let us assume that you have stored in your triangle buffer, you have stored now 2 objects, no? In the order, first the object 1 with its color and opacity, and then the second object 2 with its color and opacity. And now you push that buffer into the rendering pipeline, so the first object is grabbed from the buffer and it is then rendered. Oh yeah, sorry, no, that is yeah, I just wanted to explain it in a different way than it is given here on the slide. Okay, yeah, how can I come around that? Okay, yeah, let's go through as we explain it here, and then I can say what I just wanted to say. I wanted to explain it in a different order, but anyway. Okay, now what we do here is we now assume. Oh no, by the way, it was correct what I just said. Now we assume that the more closer object to the view plane is the object 1 with color C1 and opacity alpha 1, and the one that is further away from the view plane is the object 2 with color 2 and alpha 2. Now, how can we now render them? Okay, so here in this example we say, okay, we render the more distant fragment first into the color buffer and let its color be modulated by its opacity. No? So therefore we would just say render the object, okay, for the object, and every fragment that is generated for that object, no, we interpolate a color from the per vertex colors, and we interpolate an alpha value, an opacity value, no, both being interpolated by the rasterizer, so that now every fragment gets an interpolated color and opacity value. And we now, in a fragment shader program, no, we would just say, okay, we multiply for every fragment its interpolated color with the interpolated opacity, and that's then the final fragment color that is rendered into the color buffer. Okay. So now we would render the second object, no, the one that in our example is closer to the viewpoint. And also for that object, no, we would have a fragment shader which says, okay, we take the interpolated fragment color, we multiply it with the interpolated opacity value, and that is what we do here. And then we blend that object into the color buffer. No? And so now we have to take care, because something was already rendered into the color buffer coming from the first, the more distant object. Now, whenever there was something already in the color buffer, the color that comes from the second object now needs to be blended with that color. And if this is so, then we would just say, okay, the final color that then appears in the color buffer is just the color of the second object, or the effective color of the second object, plus 1 minus the alpha of the foreground object times the color of the background object, which was already in the color buffer. That would be the kind of blending we perform. And so the good thing about this here is, the depth test can be disabled when we perform this kind of blending. So you see here, if we can assume that we always render in the order, we call that from back to front. Back to front. rendering order, that explicitly assumes that we have sorted our objects in back to front order, so with respect to decreasing distance to the view plane, so that we can then go through or then, and if we pack if we store the object in this order in our object buffer, no, then the objects are rendered in exactly that order. And if you have two objects, then we would exactly obtain what we have here. No? First, we render the more distant object, leaving its effective color in the color buffer. Then we are rendering the more closer object, also computing its effective color, and then blending this color in the way we have shown it here with the color already in the color buffer. So now you might argue, first of all, okay, but how does the second fragment that is generated, or the fragments for the second object that is rendered, no, they perform a blending here with all the colors that are already stored in the color buffer. So why don't we do, how can we decide whether this is the foreground fragment and this is the background fragment here? No, we don't decide explicitly. No, we just say, okay, we would essentially also let the effective color of the background object, of the more distant object, be blended with the content of the color buffer. And therefore we would just say, okay, we initialize the color with 0, 0, 0, 0. So we set all the colors and the opacities initially to 0. And then we would just, when rendering this very first object here, we would just perform the very same blending. Namely, we would here say, okay, CD plus 1 minus alpha 2 times, and let us call this CI for the initial color. And you see, because the initial color was 0, this contribution is essentially 0. And now it may come out what we have in mind here, no? Because we don't want to explicitly distinguish between a foreground and a background fragment, but we want to do the very same operation for all the fragments which are rendered in the right rendering order, back to front in this example. No? And whatever fragment is rendered and at whichever position in that order it is, we want to perform the very same blend operation. No? And you see here, if we initialize the color buffer just with 0, no? Then we can just then render all the fragments in back to front order, and whenever a fragment is rendered, we do the very same operation in the fragment shader. Compute the effective fragment color by using the fragment color and multiplying it with its opacity, and then performing the blend operation which we have here and here. No? That's the very same blend operation, always adding what we have already in the color buffer with or multiplying this with 1 minus the current alpha value and adding to this the current effective color. No? And we are done. And yeah, you see here in this approach, no, we don't even need to accumulate the alpha values, no, by using the equation which we have here. No? That is not used in that back to front approach. No? Yeah, and so the problem with this is, and yeah, does it come on the next? Yeah, it comes on the next part. The problem with this approach is, but you don't come around that problem, you need to establish that back to front blending order, rendering order, sorry. And that is something that you are responsible for as a programmer. Because if you cannot enforce that the objects are rendered in that strict back to front order, if the objects are rendered arbitrarily in an arbitrary order, then the blending you perform will give an incorrect result at the very end. Because we have seen blending is not commutative. So you have to blend the objects together in a strict order. And here we choose the back to front order. And that means that we have to sort the objects in a pre-process so that then they are stored in the buffer in back to front order, so that now they are processed in exactly this order in the rasterization-based rendering pipeline. And yeah, this is what you have to do. And this then brings us to the general approach to blend multiple transparent objects correctly. First of all, you clear the color and the opacity to 0. And then you have to perform an explicit sorting operation from back to front with respect to decreasing distance to the view plane. And that is something you have to do in your application program. And that is the reason why you typically don't see, in real-time applications at least, scenes which have a huge number of semi-transparent objects. Because the transparent objects, they have to be sorted in back to front order. And it's clear that if you change the view, if you navigate through a scene, or the objects are transformed to a different position or orientation, then of course also the order of the object changes, meaning that the sorting really has to be done in every frame. And that can become computationally very intensive if you have a huge number of objects that need to be sorted. Therefore, in typical real-time applications, you only see a few transparent objects usually, because the explicit sorting of such a low number of objects can be done fairly efficiently. But if you would have to sort thousands or even tens or hundred thousands of objects in every frame, this would significantly decrease the frame times. Yeah, and now once you have established that order, that back to front order, then you can just render the object in exactly that sorted order, or you just hand over the sorted buffer objects into the pipeline, and then the objects will be rendered in the order they are stored in the buffer, and equipped with the correct blend operation, you will then just achieve what you want to achieve. Yeah, and the blend operation you use then, that is the blend operation you have here. That looks a little different to what we have discussed before. Now, let me just write it out. So what we have discussed was, we said, okay, first of all, we compute the effective color of the object that is just going to be rendered. And then we say plus 1 minus alpha s times, and then we have the destination, so alpha destination and the color destination. So you see, it looks a little different to what we have here, but so if we initialize our background with 0 everywhere, then in the first, so to say, rendering pass, where we render the first object, now you've seen what we obtain here. We just have the effective color of the first rendered object plus 1 minus its opacity times whatever is in the color buffer initially, which is 0 in our case. Okay, that means after you have rendered the first object, what you see in the color buffer will be just the effective color of the first rendered object, alpha s times cs. If now the second object is rendered, the second object again computes its effective color plus 1 minus its opacity times what is in the what is in the color buffer, and in the color buffer from the first pass, now we have that alpha, let's call it first color first, from the first object that has been rendered. And you see now that, so to say, is what we had here in the previous equations. So this equation here, if you now iteratively apply it in the correct back to front order, then this is exactly equal to the blend equations which we have introduced before. And yeah, and this blend equation that is provided by the graphics processing unit in the so-called blending stage. You can choose that particular blend equation so that now the objects are rendered with their correct opacities considered. So yeah, there's one thing. What happens now if you have multiple transparent objects and you have also opaque objects? Now it's clear that whenever you have an opaque object, whatever comes behind that opaque object should be discarded. No, it should not be rendered, because that opaque object blocks everything that shines through from behind. No? And therefore, then, in order to draw both types of objects, we just do the following. We again clear the color and the opacity in the color buffer. Then again, we sort only the transparent objects from back to front, no? So with respect to decreasing distance to the view plane. So, and what we now do is we render first only the opaque objects, and we enable, with enable depth test and right enabled. So that means that is just the classical rendering approach. No? We have opaque objects, we use the depth test, and whenever an object survives the depth test, or whenever a fragment survives the depth test, that fragment writes its own depth value into the depth buffer. That is what is meant by right enabled. Now, so that means that after 3, what we see in the color buffer is the surface points of the frontmost objects, the objects closest to the view plane, but only of all the opaque objects. In the depth buffer, we have the distance to the closest opaque objects. And now we render all the transparent objects in their sorted order with depth test enabled, and we perform the blending as we have seen it before. Now, and what does it mean that the depth test is enabled? Now, it means whenever a transparent object now wants to be rendered, it first checks whether there was an opaque object from path 3 that is closer to the view plane. If this is so, then the transparent object will just be discarded. And if that transparent object is closer to the view plane or the near plane than the opaque object that have been rendered in 3, then it is just blended with whatever color is already in the color buffer using the blend equation we have here. And we are done. So yeah, and also to tell you where this blending occurs in the graphics pipeline, also for the blending, you cannot write a shader program that performs the blending, but there's a blend stage which comes right after the depth test. So here we have the fragment shader. Then there's an output color and output opacity and output depth. And this is then for every fragment. This is then first going through the depth test. And now if that fragment survives the depth test, then comes the blend stage. And in the blend stage, we first ask, do we have enabled blending or not? And if we have enabled blending, then you see here we essentially blend 2 color contributions from the pixel shader output here. That is, so to say, the source color and alpha. Here we have the values which are already in the color buffer. We call that a render target here. Okay, and then these 2 values are compared to each other via the blend operation. And then, depending on what the operation does with these 2 color contributions, a final color is then computed, and this is the color which is actually being set into the corresponding pixel. There's a little more going on here, but in principle it is sufficient for us to just understand that the blending comes after the depth test, so it's only carried out on the fragments that survive the depth test. And then in the blend stage, the fragment, the incoming fragment color and opacity, the so-called source color and opacity, are blended with the color and opacity already in the color buffer. And then depending on the blend operation I choose, the result is computed and set as the color in the pixel. Yeah, and also here a little bit about how we can control that blend stage. It is enabled via DX calls and performed automatically. And again, also here color and alpha values in the color buffer cannot be accessed directly, so we cannot read them out in a shader program and do something with them. And here's now how you can control what should be performed in that blend stage. For instance, first of all, you can set the blend enable to true. That means blending should happen. Or you could just also disable it by saying it's false. Then no blending at all would happen. And then you can determine the blend operation you want to perform. Let me go first to this last call here. Now here you set the blend operation that should be performed by the blend stage to blend op add. That means that the contribution from the source and from the destination are just added together, as you see here. And then you can also say, okay, how should the source contribution be computed and how should the destination contribution be computed? And here we say blend source alpha for the source blend. And this essentially means that the source color is multiplied by the source alpha. That is what you have here. Then for the destination, you say you want to have a blend inf source alpha. That simply means that you want to take 1 minus the source alpha as the modulating factor for the destination. And then you just add the both contributions together. And you see that this is exactly now the blend equation that we want to use, supported by the blend stage. And if we now render the objects in the correct, we call that visibility order from back to front, then we obtain the blending as we want it. Okay. Yeah, what we will discuss next is texture mapping. We have already discussed texture mapping to a certain extent, but we will in particular look at how now a texture is sampled in a fragment shader program or in a vertex program. And then we will in particular look at what we mean by texture filtering and MIP mapping, because these are very important concepts in texture mapping. And if you don't make use of these concepts, in particular MIP mapping, then you will never get a very pleasant quality when rendering a texture mapped object.